So we're looking at Chapter 6. We're going to do a quick overview of Chapter 6, which is differential equations and slope fields. So the first thing we talked about was determining if an equation is a solution to a differential equation. So if I look at, so say I have y equals 2/5 e to the negative 4x plus e to the x. And we want to know, is that a solution to y double prime plus 4y prime equal 2e to the x. So if I look at this, what it's asking me is I need to take the second derivative, well, I need to take the first derivative and then the second derivative and plug those in and see if it gives me this, then yes, it's a solution. If it doesn't, then no. So if I look at this, our first derivative, so I've got that 2/5. I've got e to the negative 4x times negative 4 plus e to the x. So my second derivative, still have my 2/5. E to the negative 4x times negative 4, but I've already got a negative 4 there, so it's 16. E to the x. So now I'm going to take these two, plug them in, and see if they work. So my second derivative, so I've got 2/5, e to the negative 16, e to the negative 4x, plus e to the x, and I've got a plus 4, 2/5, negative 4, e to the negative 4x, plus e to the x. Okay. So let's look at this. Let's try to simplify it down. I can factor 2/5 out front. So I've got 16 e to the negative 4x plus e to the x. Here, if I multiply those, it's going to give me negative 16 e to the negative 4x, and then plus 4 e to the x. So these two would cancel. That's going to give me 5 e to the x. Those would cancel and gives me 2 e to the x, which is what I'm looking for. So yes, it's a solution. Oh, and you couldn't see that, sorry. I didn't move it up. So we said these two canceled. We could add these two together. 5s would cancel, and you end up with this. So yes, it's a solution. So let's look at one more. So what if I have y is x squared e to the x minus 5x squared. We want to know, is it a solution to x, y prime, minus 2y equals x cubed e to the x. All right, so what we need is our first derivative and our original. So we have our original, so let's find our first derivative. We're using our product rule here, so I've got the first one times the derivative of the second, which is just e to the x, plus the second one times the derivative of the first, which would be 2x, plus, oops, that's supposed to be a minus, bring my 2 down, so it's 10x. Okay, so let's plug that in. So I've got x times x squared e to the x plus 2x e to the x minus 10x minus, we've got 2 times our original, so it's x squared e to the x minus 5x squared. All right, so let's see if that gives us x cubed e to the x. So we're going to distribute our x, so it's x cubed e to the x, 2x squared e to the x minus 10x squared. Let's distribute our 2, so it's negative 2x squared e to the x plus 10x squared. So if I look at this, these two can cancel, these two can cancel, and I end up with x cubed e to the x. So again, yes, that is a solution. All right, so one of the other things we looked at was slope fields. So what a slope field is just an equation. It's actually just a graph of our slopes. So say I have y prime, my first derivative is equal to x. Okay, so my first derivative is equal to x. So what I'm going to graph is basically a picture of my slopes. So let's see, I have a graph. So let's see, if I plug in 0 for x, 0 is just going to give me 0. So it means for any x that's equal to 0, my slope is 0. So I'm just going to draw some 0 slopes in here. Now if I look at 1, if I plug in 1, my slope is 1. So let's see, I've got a slope of 1 here, slope of 1. And I'm not drawing this too great, but so those are all slopes of 1. If I plug in 2, my slope is 2, so it's going to be a little steeper. Plugged in 3 is going to be even steeper, so it's going to give me 3. Now if I come over here to -1, my slope is -1, so it's over here. I've got a negative slope. If I plug in -2, my slope is -2, so it's even steeper. And so if we're kind of looking at this, we've got these 0 slopes in here. What does this kind of look like? Which I really didn't graph this very good. But if I was kind of following, say I pick a point, and I kind of followed my curve, it looks like a parabola. If I can pick any point I want and follow the curve, and it looks like a parabola. So let's look at this. So if I had, this is dy over dx. If I took the antiderivative of this, so let's say I separate my x's and y's. Let me slide that up a little bit. Move my dx over here. My antiderivative of y is y. So I'm going to write that over here. So it's y. My antiderivative of x would be x squared over 2. We'll say plus c. Well, this is a parabola, or this is a quadratic function, so my graph is a parabola. So my slopes will give me kind of a glimpse of what the antiderivative, the function, is going to look like. So let's look at, I'm going to bring the book over here, so because you can tell my drawing is not the best. So let's look at some in the book. Okay. So say we're looking at these, and we're matching. This is wanting us to match. So notice that, like the example I had, everything just involves an x. So that means that they're all the same all the way down. And so if we're trying to match these, let's just start with this one. Notice at 0, my slope is undefined. And then these are positive slopes. Those are negative slopes. So if I'm looking at these 4 choices I have down here, which one would have the slope of undefined at 0? Well, obviously this one. Okay? Because you can't plug 0, we can't divide by 0 and get a real number. So my A would go with 60. Now if I look at B here, my slope is showing me these little blue lines would be 0. So if I'm looking, that's the only one that's got a slope of 0 at 0. So if I plug in 0 to these, let's see, this is going to give me a 1/2. It's going to give me a 1. So this is going to give me a 0. So it works. So my B would have to go with this one. Notice also if you were to graph this, it looks like a cosine function, which is perfect, or it's actually negative cosine, because the antiderivative of sine is negative cosine. So this one, we've got a positive slope at 0, positive slope at 0. But if I'm looking at it, if I kind of drew a graph, it looks like we've got a sine curve. So we know it would have to match up with this one, because the antiderivative of cosine would be sine. So we're kind of left with this one. And we could kind of check it. If I plugged in 0, I'd get a 1. If I plugged in, say, a 1, what is e to the negative? Oh, sorry, negative 1. That's going to be about 7. Look at that. That's a pretty steep slope there, 1. If I plugged in a positive 1, you're going to get a pretty flat slope, because the larger the numbers, the closer this is getting to 0. Okay, the more negative numbers, that means our exponent is getting bigger, the closer it is to undefined. So we're able to kind of match them up. Now, we also could have some that look like these. Sorry, my book's dirty. You can see a fingerprint. Where these are mixtures of x's and y's. So they've already kind of got them matched up for us. They're just kind of showing us. But if we're trying to match them, again, what we could do is plug in points for x and y. So they've got us a chart. Plug in points and look at the graph. So say I plugged in -4, 2 to this one. So I've got 2 minus a negative 4, so 6. So at the point negative 4, positive 2, my slope is very, very steep. It would be at 6. Now if I plugged in negative 2, 0, so negative 2, 0, if I plug that in here, that's going to give me a 4. Still, my slope is very steep. If I plugged in 0, 4, again, my slope is steep. So now if I come over here, what if I plugged in the point 1, 1? Plug in the point 1, 1 here. That's going to give me a 0. And notice I've got a 0 slope here. If I plugged in the point, let's see, 2, 3. So right here, 2, 3. Looks like a positive 1. If I plugged in 2, 3, so it's 3 minus 2, it's going to give me a positive 1. So we're just kind of looking at those points and seeing what does it go with. Okay? Now the last thing, oh, no, I'm not to the last thing yet. We also talked about rate of change. So here, I'll just get a new piece of paper. So let me see, what if I have an equation that says the rate of change of y, or anything we want it to be, we'll say y, is proportional. Let's see if I can spell. There we go. Proportional to y. Okay, so the rate of change of y is proportional to y. So the rate of change, remember, is our slope. So it's our change in y over, let's say time. Let's say we're proportional. It doesn't tell us. We're going to say it's proportional to time. Rate of change of y with respect to time. So it's a direct variation. So remember from algebra, if we said that y is proportional to x, we'd say y equals kx. So here we're going to say the rate of change of y is proportional to k times y. So now we're going to use our separation of variables, and we're going to solve this to find our actual equation. So what I'm going to do is get all my y's on one side, all my other variable would be t, all my t's on the other. So I'm going to divide by y, so I'd have dy over y equals k dt. Now k, remember, is a constant. It's not a variable. So when I take the antiderivative of this, it's like a 2 or a 3. We're actually just going to attach a t to it. So we're just going to take the antiderivative of both sides. Now this side, that's a perfect natural log. So I've got the natural log of y equals, if I take the antiderivative of this, I'm going to get a kt. And then I always add a plus c. Now I do not have to add a plus c to both sides because we'd wanted to get them together. This is a constant. If I had a constant over here and subtracted it over, they're not going to cancel. They may not be the same constant. So I've got a constant minus a constant, it's just a constant. So we're just going to put a constant on one side. So now if we're going to solve for y, to get rid of natural log, we take e to both sides. So these two would cancel, and I'd have y equals e to the kt plus c. All right, so now this, I'm going to separate this a little bit because remember our exponents, if I'm adding them, I can separate them using multiplication.